So good morning. We will start today's lecture series of this GIAN course with my lecture on multiferroics and magnetoelectrics and what is their application in terms of IoT and the smart world. So before I start, I want to thank Professor Srinivasan for accepting this GIAN course with me, and also I am thankful for the GIAN organizers for providing me opportunity to share this course with distinguished Professor Gopalan Srinivasan. With this, I would like to start my talk today. So sustainability is a buzzword, right? And we all are worried about sustainability. So what is our contribution as a scientist and researcher towards sustainability is very important to understand. We are progressing towards a smart world. We are trying to make things smart. We are developing the technology, but there is a cost. So what is that cost? So let's see. So we have a desire of the smart world. We all know, right? We want to make everything smart. So we are looking for smart cities, smart hospitals, smart surroundings, smart working place and whatnot. See, this is what we are at right now. Everything is smart and this is what we desired. But how do we achieve that smartness? So I'll talk about a very small example, very crude example. Suppose you have some problem with your medical condition, you have high blood pressure or you have high pulse rate, but you need to be monitored and your doctor is not available 24/7 in front of you physically. But if you are wearing a device, a sensor, sir talked about yesterday, some sensor which can sense your cardiac condition, something that can sense your blood pressure and which you are wearing. So wearable electronics is the name for that thing, and then the doctor, wherever he is in the world, he can access it through internet. But for that it has to be connected, right? Everything has to be connected to the other things. So how do we connect all these things? So everything is connected to everything. That means lots and lots of microelectronics needs to be installed, lots and lots of sensors needs to be installed. Not only installed, but they need some energy to run, right? So this is how we do. We connect everything to everything and we create a digital nervous system where everything can communicate to everything. So your car can communicate to your home, your wearable electronic device can communicate to the hospital with your doctor and many other things, right? So this is how it works. But what are the challenges? So if you see this, about 30 billion sensor connected by 2020 already. We are in 2024 and 212 billion total number of available sensor enabled objects are there. What does it mean? 212 billion is actually 28 times the total population of the world. So the people are less, but the sensor and the microelectronic devices are more. And it means it is projected that by 2030 we will be needing 40 to 50% of the energy to run that, and we are going towards that. So what is desirable? The sustainability is the desirable thing, and we need to have responsible energy consumption, affordability and sustainability, right? So what is the solution? How to achieve that? So this is the future sensor trends for everything pretty much. And if you see, since we are focusing on magnetoelectric materials and multiferroic materials, so magnetic and electric combine together make 14% of the sensor which can be used in Internet of Things, right? So we need sensors. We can use magnetoelectric sensors, but what qualities we want in those sensors? So we actually want them to be cheaper, possible. We can work around and we can get the material which is cheap. It has to be more power efficient. We can work in the scientific way and we can find out the ways to work, and we can have some more power efficient sensors, and it should be easy to use. That also can be looked around. But can we make them smaller and smaller? Can we scale down them to so much? So that is the task that we need to look at. And materials and devices that we need to work for Internet of Things should be compact, low voltage, low power and low leakage. So this all needs to be achieved to sustain the world that we are progressing towards, right? So electromagnetic devices are desirable because we have seen the trend, and electric and magnetic sensors are desirable and they are useful in various applications. But we need to scale down the device. So can we scale down the device is the question. So scaling of device, Gordon Moore, who was a director of research and development and Fairchild Semiconductors, and he was also a co-founder of Intel Corporation, he published a paper where he claimed that in every year, initially he said every year, the number of transistors are doubling and on a microchip, and that's how the speed of computer is doubling every year. But it was in 65 that he claimed that, and then in 75 he revised that and he said every 2 years it will be double, the number of transistor on a microchip. This is not a law, but we call it Moore's law. It was predicted, and it comes out that it was true. It actually became valid when we looked at the years behind. So initially it was electromechanical device which used to work as a transistor. Then we had relay. See, if you notice the size and the year, then you can see how we evolve and how we have scaled down the devices. Then we came to the transistor, which we also these days see in the labs which you work with, and then it came the microchip. So you see the microchip came around 75 here, right? That's when he revised his paper, and then from then onwards it held true. So if you see the size of the transistor over time, you see the typical size is mentioned on the y-axis and the year. So by now we are at the limit of single atom. We cannot go beyond that, right? You can miniaturize a thing, but not beyond the limit of the atomic scale. So we are here. Now what is next? We need to miniaturize, we need to increase the speed, we need to store more data, we need to make things work, we need to make things connect, but what do we do for that? So what does it mean? See, 2015, the size of the transistor was 10 nanometer. In 2017, it was 7 nanometer. And then we are here. So again, what I am repeating, that what do we do, how to achieve? So at present, what do we do? At present, we use charge of electron to encode the information, right? 0 and 1. You are very well aware that binary codes and all this. Yes, yes, please, ma'am.
Is there any lower limit for scale down approach?
Yes, beyond atomic level you cannot go, right?
Revise the device at that atomic level?
No, the size of transistor can reach a little less than that, but I don't think device can be of that size.
Because I had read something 4 nanometer is the limit length.
Okay.
Not less than that.
Right.
Is it true?
I am not certain, sir.
Because
do you have?
I am not that much familiar with the electronics part of this.
Right. Yeah, so I think I am not certain at this point. I also need to look at it. But sir, if you have any comment, please.
Somewhere in research paper I had read it.
Okay.
4 nanometer is the limit. But they had not given the reason, valid reason for why 4 nanometer is the limit.
Okay. So we need to look into it together. Yeah. So at present we use the charge, as I said, binary numbers, you are aware. What about if we also start using the spin of the electron? So that may work out in our favor, right? So there will be another fundamental unit which can be used to code and decode the information. So what is spin? We all know every electron has a spin, and an electron can have 2 values of the spin, that we know. So electron actually behaves like a tiny magnet. So how those spins are aligned in a material, that decides the magnetic behavior of that material, right? So if they are randomly aligned, it is paramagnetic. Yesterday we talked about it, and this is the behavior of MH curve, so magnetization versus applied magnetic field, and the chi-t, susceptibility as a function of temperature. This is what you get when you have a paramagnetic material. Then ferromagnetic, when the spins are aligned parallelly, and then that's what you get, and this is what you get. So Tc is the Curie temperature. Beyond this temperature, a ferromagnetic material behaves like a paramagnetic material, and below this temperature they are ordered in parallel fashion. Similarly, antiferromagnetic materials, spins are anti-parallel, but then when you consider, so for antiferromagnetic materials, the critical temperature is named as Néel temperature. It is as good as Curie temperature, but in antiferromagnetic materials, and here the material beyond Néel temperature behaves like a paramagnetic material, right. So this is the magnetic ordering which we can use. Now electric ordering, we are aware there is a dipole, and that, so similarly electric order can also be paraelectric when the poles are not very well aligned, and that's how it is, okay. So it is analogous to material. Now the task is, can we combine a ferromagnet and ferroelectric? If we can, then can the properties be combined? You can combine two materials, but then the properties also can be combined. So if you combine a ferromagnetic with a ferroelectric, you can achieve a multiferroic material, because it has two ferroic orders, ferroelectric and ferromagnetic, in the same material, right. So electric field, now combining is not enough, you have to achieve the coupling between these two. So to achieve the coupling between ferromagnet and ferroelectric material, you need to work out with the science and with the understanding of the structure and various factors like critical temperature, how the intrinsic properties are working, and other things. So what is the rationale? Multiferroicity is achievable on paper, yes, we can achieve it, but it is difficult to achieve in a single phase material. Why it is difficult? Because see, for a material to be ferromagnet, you need partially filled d orbital, right. You need spins which can contribute to the magnetization. So partially filled d orbital you need. And for ferroelectricity to exist, you need empty or fully filled d orbitals. So this is mutually exclusive, right. In a single material, this is not achievable. So this is the problem which is very well known in the multiferroic and magnetoelectric community, that this is chemical incompatibility. Now ferroelectrics needs to be insulating for polarization to exist, and ferromagnets often are conducting materials. So it is not easy to achieve in the single material. So how to combine ferroelectricity and magnetism in one material is the task. So let's see. If it is collinear, there is no magnetic moment, right. If it is anti-parallel spins, two electrons are anti-parallelly aligned, then you cannot have. But what if they are canted? So if they are canted, you get some resultant of magnetization, right, because they are not completely cancelling each other here. So you get some magnetization. So canted spin can result in a magnetic moment, okay. Bismuth ferrite is an example which sir discussed yesterday. See, so here is the example, and iron is the contributing factor for the magnetization in bismuth ferrite. And in bismuth, so see, there are two different atoms which are contributing to magnetization and ferroelectricity. So bismuth is contributing for ferroelectricity in bismuth ferrite, and iron is contributing towards the magnetization. So bismuth has 6s2 lone pair electron which are responsible for the polarization, okay. Now bismuth ferrite, so good, we have a material bismuth ferrite, it tweaks the criteria for multiferroicity. It is at room temperature, what data is achieved. It is ferromagnet and ferroelectric. Then what is the problem? We have a material, but there is a problem. It has high leakage current, so it is not a very good ferroelectric material, right? It has weak coupling between magnetic and electric. What does it mean, weak coupling? That means if you change the electric field, you cannot control the magnetization, or if you change the magnetic field, you cannot control the polarization, right? So that is the difference, and that coupling needs to be achieved. That is the whole idea. You can have a material, you can have, but if they are not coupled, if they are not acting at the same time, and if they are not interconnected so that you can control one by another and the other by first, then there is no point. So it cannot be effectively basically used in the devices, right? So bismuth ferrite was existing, but it cannot be used. So what are the ways to achieve multiferroicity? So one thing is we find materials like bismuth ferrite by understanding the structure, and in single phase we try to achieve the multiferroicity, or we combine the two materials and then find the way around, right? So I will discuss both the cases very briefly. So we in our group we have been working in rare earth orthoferrites for the reason that rare earth ferrites give us a good opportunity for 3D 4F interaction. So see, if RFeO3, so rare earth has 4F orbitals. If you go from here lanthanide to lutetium, you get differently filled F orbital, right? And you have iron which has D orbital partially filled. So 3D in iron and 4F in lanthanide. So 3D 4F interaction gives us an opportunity for complex magnetic and electronic behavior to exist and to analyze also by understanding the dynamics of 3D 4F. So here we have worked on samarium orthoferrite SMFeO3. We pick up samarium and we investigated it, and finally we found out that there is a twist in polarization. I have named it a little to make it interesting. There is no twist, we just found out that if there was exchange in striction, so there is magnetic interaction between D and F block elements and they induce the polarization. So they have induced the polarization in samarium orthoferrite, and we further investigated. This is the structure. It is distorted perovskite. It is orthorhombic. Space group is PNMA, or it is also represented with PBNM, and these are the lattice parameters. So we have looked for canted antiferromagnet whether it is existing or not. We have looked for exchange interaction. We actually found out it does exist, and D and F orbital interactions was seen. So we could say that there is a possibility of multiferroicity. So we synthesize it at nanoscale using sol-gel method, and we prepared nanoparticles which were under 100 nanometer size, and it was confirmed about 65 nanometer average size, and we confirmed the elemental existence. Samarium, iron and oxygen were in the proportion, so it was confirmed. Then we saw that there is a transition at 480, as you see this here, 480 degree. 480 degree Kelvin, there is a transition which is a spin reorientation transition. So spins are reorienting at that transition to understand it. Then we also saw that permittivity has some changes at 480. So that means this is magnetic behavior here, where spin reorientation is taking place at 480, and similarly here you see there is a sharp transition for the permittivity in terms of temperature at exactly same temperature 480. That means simultaneous ferromagnetic and ferroelectric behavior is observed near room temperature, right? So, now we try to find out, is there a link between these with the structure? Is structure playing a role? So, structure is a crucial thing to decide the properties of any material, physical properties. So, we looked into the link through atomic vibration. So, we were looking for spin-phonon coupling. You must have read a lot of times what is spin-phonon coupling, right? So, phonons are nothing but they are discrete unit of crystal vibration. So, this is how, if a crystal is existing and these kind of vibration, this is phonon. This is the effect of phonon on crystal, and that's with phonon you can measure the vibration in the crystal. I am saying it very crudely. So, Raman effect is a way to measure the spin-phonon coupling. So, what happens, if incident light is put on a sample and it reflects the same wavelength, it is Rayleigh scattering, right. But if the wavelength is less, then it is Stokes-Raman scattering, and if wavelength is wavelength is short, then it is anti-Stokes, and if wavelength is longer, it is Stokes. So, this technique, Raman's technique, we used, and this also tells us that incident light induces molecular vibration. So, Raman's technique is based on this fact that incident light induces molecular vibration, and then wavelength of scattered light changes. It will be either Stokes or anti-Stokes, and then it is a Raman scattering. So, see, if these are the magnetic spins, right here, and if there is effect of phonons, if there is incident light, then this is spin-phonon coupling effect. So, vibration of the atom also contribute in the spin, and that is what gives you spin-phonon coupling. And how do we measure? We measure it with Raman spectra. This is just a animation to make you understand how it affects, how the spins are affected when the phonon is existing and spin and phonon are coupling. So, we do Raman spectra, and then we take data from this spectra and plot it in terms of Raman shift. So, see, this is Raman shift of 150 to 246, and then here we have plotted this, and you see again at 480 degree there is anomaly, right. That means spin-phonon coupling is taking place. So, it kind of confirmed that structure is playing a role at 480 degree, where we are getting the connection between ferroelectricity and ferromagnetism. So, finally, we could conclude that there is a possibility of multiferroicity in samarium orthoferrite at 480 degree Kelvin, and spin and phonon coupling are contributing in that effect. Another example of rare earth ferrite which we studied is lutetium ferrite, where again I was intrigued with the 3D 4F dynamics of rare earth ferrite, and we worked, and it was very interesting. We tried to synthesize nanomaterials, and we thought we will do the different morphology of the two materials. So, we prepared nanoparticles, we also prepared nanofibers. Now, nanofibers are drawn, so there is strain associated with the forming of the nanofibers, right. And nanoparticles, as you know, they are quantum confined materials, so there is already property change in comparison to bulk. So, we wanted to see how, as compared to bulk, the properties will change, whether it is nanoparticle and nanofiber, and is there any difference in nanoparticle and nanofiber. So, we synthesized. Then we were trying to find out what structure it is. The structure supposed to be orthorhombic, but it was not orthorhombic. We were investigating and we were seeing there are few extra peaks, and we were not able to find out what it is. And I was telling my colleague all the time that we need to resynthesize, it is not pure, we need to resynthesize, it is not pure, and we did 10 times, and every time we got the same result. Later one day we were sitting and matching the peaks, and then we thought, why don't we match it with the hexagonal part of hexagonal lutetium orthoferrite, and we did, and everything was matched. So there was a combination of orthorhombic and hexagonal in the same material. So we got more interested, okay, we should investigate this instead, and we realized when we do the Rietveld analysis of the X-ray diffraction data, the structural data, what we found was in nanoparticle, you see, nanoparticle we got 73% of orthorhombic and 27% of hexagonal, and in nanofiber it is exactly opposite, while they were synthesized at the same temperature. So we tried to understand, and we concluded that it is the strain which is associated in synthesis of nanofiber is contributing, and that is why it is favoring the hexagonal phase in the nanofibers. So hexagonal is dominant in nanofiber. Now we also investigated Raman, and we found that in both the cases orthorhombic and hexagonal both are existing. Now next we tried to see what is the distortion in octahedra. So using Rietveld analysis, we also checked the bond lengths here, you know. So it's a powerful tool, X-ray diffraction is a powerful tool, you can do so much with that. So we tried to see what is the distortion in terms of orthorhombic and hexagonal, and we did find that there is considerable distortion which may contribute in the physical properties, because the structure is a very much driven thing by the bond lengths and other things, and the physical properties are related to the structure. So we did TEM. We realized that the sizes and everything is under the range which can be called nano, and then we also found out with the high resolution TEM that and diffraction pattern that both the phases are existing in the material. So it was very well confirmed. Then we observed the magnetic behavior, and if you see it is the same material, lutetium, iron, oxygen, but you have different magnetic behavior for the nanoparticles and for the nanofibers. Further, we did Exane's experiment at the synchrotron, where you can probe the local environment. So Exane's is nothing but it measures the fine structure of X-ray absorption near an absorption edge, and this region is typically 10 electron volt to 20 electron volt. So in that range you can probe the material and you can take the edges. So for example, if you want to measure the iron L edge, so you can L1, L2, L3 edges, you can decide which edge may be contributing, and you can probe it between 10 electron volt and 20 electron volt, and you get the information about the local structure. So we could calculate eventually using this experiment the crystal field splitting at different temperature of the material. So if you see, the green one is nanoparticle and this is nanofiber. So crystal field splitting is less in case of nanofiber, and here it is more in terms of nanoparticle. This is what we calculated, and this also contributed in understanding the unusual behavior of magnetization. We again further checked the polarization, and then we found out that they are showing some polarization, but for nanofiber it is more impressive than nanoparticle. So nanofibers were superior in terms of polarization. So we tried to look into the nanogenerator, triboelectric nanogenerator application, and impact force of 21 Newton and frequency of 10 Hertz we used to create the impact, and we realized that 3.4 volt we can generate for nanoparticles, and we could generate 6.7 volt for nanofibers, right. And the maximum value of current density for nanofibers is 15.9 microampere per centimeter cube, and for nanoparticle it was 0.38 milliwatt centimeter per centimeter cube, it was the power density. So we found out that just by the structure in case of samarium orthoferrite and just by the understanding the morphology, change in morphology gave us understanding that morphology also plays a crucial role in deciding the properties. It was very evident in including the magnetic behavior and also the application as a triboelectric nanogenerator. Then very briefly I will go with a composite which we created. We created HFO, which is holmium orthoferrite, and BTO composite. We did the same thing, but we made the nanofibers which were heterostructure. So, we had one layer of HFO, over that one layer of BTO, then HFO, then BTO. So, this way we created a heterostructure which was not very uniform. So, HFO and BTO thicknesses were different. So, it was a heterostructure that was created, and then we investigated with the parent compounds HFO and BTO and we compared. So, you see the magnetism of heterostructure is actually intermediate between the parent constituent. HFO is highly magnetic material while BTO is not. So, in the heterostructure we could get something intermediate which was expected. Similarly, we could get the polarization, and then further we checked other parameters which were well in consent, and then you see we calculated the power here, voltage generated. So, HFO is generating up to 2.5 volt, BTO is generating, but when you combine them the performance is enhanced, right. And similarly, the power density is also more than double of any of the parent compound. So, we have with whatever work we have done, we have seen the nano-composite, we have seen the single phase materials, but ferroelectricity was the achievable thing. So, these are the some conclusions, and with that this is what I wanted to share. If you have any questions, I am here to take them. Anything at all? If not, then I want to thank all my mentors, colleagues and co-workers who have been constantly supporting me. Okay, thank you for your attention and time.
Preparing this microstructures. What about the connectivity of
So, we are doing electrospinning. Yeah, so we are collecting the fibers on a electrode. So, they just go there and sit there one over another, and then we anneal. So, they are well aligned and well connected.
Otherwise, connectivity.
Yeah. So, it's not that we are taking two separate materials and connecting. So, we are synthesizing them together through electrospinning.
So, three-dimensionally and not to get connected to each other.
What?
Fiber
So, I
is
have
one
not.
dimension, okay. Fiber
Yes.
is one dimension.
Yeah. So, we have not shown you the SEM, but I can share that with you later.
Just
how
out
it
of
looks.
curiosity.
Yes, yes, yes. I will share it. Yes.
What is exchange friction?
Exchange friction is like, okay. So, when dipoles, I will not go into that, when dipoles are aligned, right, but if they are slightly canted, there is exchange of dipole moment among them, and that causes the friction in the material, and that causes the polarization in the material, in simple words. So that is what exchange. Sir, maybe you can add something in exchange restriction. How to explain it better, the exchange restriction. Yes, in ferroelectricity. So this is what the understanding, basic understanding of exchange restriction. Like magnetorestriction. So in ferroelectric material, you can use that to understand
Is
that.
this electrorestriction analogous to that?
Exchange restriction that we are talking about right now. Okay? The next lecture is L4.
Is this my presentation?
Okay, yeah. Right, okay. All right, so this will be the final talk on thick film, multi-layers or bilayers. From tomorrow onwards, I'm going to focus only on nano-composites, like nanoparticles and fibers, and then applications. So I did discuss some of these yesterday when we talked about multiferroic phenomena, theory and measurements. So this one will wrap up most of the stuff that you need to know regarding thick film composites essentially. Okay. So as I mentioned, you have a very wide choice for the ferromagnetic phase. So as you know, the 3D transition metals, they are abundant and they can be used in all of these composites. So I'll discuss some of the data we got on composites with iron, cobalt or nickel. Then on the alloy systems, primarily on permandur, terphenol D, galphenol and med glass. And some ferrites including spinels and hexagonal ferrites. So the systems I'm going to discuss, they can have either a ferroelectric phase or pure piezoelectric. And you are already familiar with barium titanate, PZT, PM and PT. These are very popular ferroelectrics to use in the composites. And also the piezoelectrics that could be used are quartz, aluminum nitride, gallium nitride, gallium arsenide, and lanthanum gallium tantalate and lanthanum gallium silicates. They are not readily available. It's very hard to get those single crystals, but we were able to get them. But I'll show you just some of the results we got in composites based on LGT and LGS. And PVDF is a polymer ferroelectric. So, when you want to put together a composite structure on a flexible substrate, that is the material to go with. It is very easy to make anything that can be deformable, so on a flexible substrate. So, the key results I am going to focus only on low frequency and resonance magnetoelectric effects. Right, some of the key parameters that you need to know for the ferroelectric and the ferromagnetic are in the next two slides. Here I show the piezoelectric coupling constant in the direction parallel to the electric field or polarization, that is D33, and D31 is the component that is effective perpendicular to D33, that is D31. It is usually 1/2 of D33 with a negative sign. And also other parameters are the dielectric constant, Curie temperature, density, resistivity, and mechanical resonance coupling coefficient K33. These are related to either longitudinal acoustic resonance or bending resonance. So, as you see here, barium titanate has D33 of close to 200, PCT has a much higher value, and in PCT they substitute many materials to make what are called soft PCT and hard PCT. Soft PCT has low dielectric constant and high D33. The hard ones have lower D33, but much higher dielectric constant. These are different types of PCTs used for a variety of applications. The Navy in the US, they were interested in using PCT for sonars and other devices. So, people came up with a proper substitution to get the desired parameters. So, it has a variety of substitutions, you do not have to worry about it. These numbers do not mean anything, PCT 5, 4, but some are hard, some are soft, and they can have very differing properties. Okay. And PCT has usually Curie temperature well above room temperature, above 300 degrees Celsius, and the relaxer ferroelectrics, both PMNPT and PZNPT, they have pretty good D33 values, very high dielectric constant, but very low Curie temperature compared to PCT. So, anything to do with high temperature applications, the relaxer ferroelectrics, they are not the ones you want to use. Okay. And PVDF is it's rather low D33, but it has a better Curie temperature compared to PMNPT. But as I said, the advantage is it is very flexible, it is a polymer. And some of the ferrites and the alloys, the parameters are listed here, magnetostriction, density, and the mechanical coupling factor, and the and what else, resistivity and Curie temperature. The Curie temperature is high enough, you do not have to worry about any threshold limit for the applications, because they are well above room temperature, they can be used even if you go 100 degrees above the room temperature, that is fine. And terphenol D has the disadvantage of very susceptible to getting oxidized if you expose it to air. So, it always needs a protective coating, and it is very hard to machine, you cannot cut it or do any proper machining. But on the other hand, galphenol is quite good, it is not susceptible to oxidation, it has a much higher magnetostriction compared to all the oxides. And med glass is also very nice material to use for applications such as a variety of sensors, mid glass and aluminum nitride. They are useful for especially magnetic field sensors. All right, so I will talk about the low frequency magnetoelectric effect and the resonance one, both bending and acoustic modes along the length, width or the thickness. And this you have seen a couple of times yesterday. This is a setup we use for the low frequency magnetoelectric voltage measurements. So, you need a bias field generated by an electromagnet or a solenoid, and AC field generated by a solenoid or Helmholtz coils. And then you have to power the electromagnet and the Helmholtz coil with AC, DC and AC. And the detection, you can measure it with a scope or a lock-in amplifier. Then depending on the field orientation, you have voltage coefficients defined as transverse or longitudinal. Right. So, let us see what are the systems. I will go through the list here. Ferromagnetic alloys and metals with PZT and PM&PT, then ferrites with these two, both spinels and hexagonal ferrites. And also I will talk about some of the example systems with pure piezoelectrics, including LGT, LGS, quartz, and aluminum nitride, gallium nitride and gallium arsenide. Okay, so as you know, among the 3D transition metals, nickel has the highest magnetostriction and the highest piezomagnetic coefficient. As you see here, it has negative magnetostriction parallel to the applied magnetic field. In the perpendicular direction, it is positive, about 1/2 of lambda 1,1. And the Q value for in-plane magnetic fields, you want to find out Q11 plus Q12. This is the slope of lambda versus h, which is Q11 plus Q12 as a function of the static magnetic field. And so, these are the tri-layers of nickel, PZT nickel, or cobalt, PZT cobalt, and iron, PZT and iron. As you see here, with nickel, you have very high magnetoelectric voltage coefficient. So, the maximum value is around 500, and of course, the value drops down to 0 when you have saturation of the magnetostriction. Cobalt, the key observation here is when you increase the static field from 0, it peaks up, then it keeps decreasing as the slope goes down, and then it reaches near 0 value. But on the decreasing field side, there is a hysteresis, it keeps going up here. So, this is very common with cobalt, it has very high anisotropy. So, it retains, it has some kind of a memory effect. So, the magnetostriction for increasing and decreasing fields, they are not the same. The slope is also not the same. That is the reason you have the hysteresis for going up in field and then coming back down. Iron, it has very peculiar characteristics. The magnetoelectric voltage coefficient has a small hysteresis around 0 static field, then it reaches maximum, then there is a change in the sign around here. This is all, they essentially track how Q changes with H. Okay. So, this hysteresis and this reversal in sign, it is due to the way Q varies with the bias magnetic field. Positive and negative does not mean much. When you measure the phase, there is a phase change of 180 degrees for positive and negative values, that is all. The voltage still they remain the same. Okay. And these are the resonance magnetoelectric effects. In a case of the symmetric tri-layers, there is no bending resonance, it is only the longitudinal acoustic resonance, and there are two different scales. On the right, you have the scale for cobalt, PCT cobalt. On the left, it is the scale for nickel and iron. As you see here, for nickel trilayer with PCT, the maximum value at resonance is as high as 80 volts per centimeter It is very high, and this is the kind of values you want for applications related to sensors and so on. But cobalt is also not very high. It is much on the order of 10. Yeah, it's about 9 volts per centimeter stirred. Iron is much higher than cobalt. It's about 45. So among the 3D transition metals, nickel has the highest value. But I want to caution you, nickel, when they make the nickel platelets, you can do quite a few things. Anneal the nickel platelet, or the way they prepare it, they can apply a pressure or apply some gas, atmospheric gas, or argon. A mix of all these conditions would change the properties quite a lot. It changes the magnetization, anisotropy, and the magnetostriction. So depending on how nickel alloy was made, the things are going to be much different. These values are not universal. It depends on the sample preparation history. Okay? So all these metals and alloys, you have to be very careful. But from the manufacturer, you can get all the data on the magnetic properties or anything of interest. It comes with the specifications are available from the vendors. This is another example where you have a film of PCT deposited on nickel. There is a gold plate, and then there is a nickel layer, and PCT was prepared by pulsed laser deposition from a target of PCT onto nickel. Then they made some gold micro darts for electrical connection, and this one is the polarization versus electric field for the PCT film, and it has reasonably good value for the polarization. But what's important here is what is the induced magnetoelectric voltage as a function of the bias field, and this is the PCT film sputtered at a partial pressure of 100 millitorr. I am pretty sure that this has to be deposited in oxygen atmosphere, because PCT is essentially an oxide. So you need oxygen during the deposition process. And the induced voltage is around 5.25 millivolts. We don't know the thickness of the PCT layer. So what's available here is just the mu voltage coefficient. Just to give you an example. Okay. So permandur is an alloy of iron, cobalt, and a very small amount of vanadium. It has high permeability and high magnetostriction. The magnetostriction is positive, and this is the piezomagnetic coefficient for in-plane magnetic fields. It's quite good, on the order of 0.05 times 10 power minus 6. And when you make the composite, it's probably as good as nickel. This is the voltage coefficient versus the static field for in-plane fields and fields perpendicular to this trilayer. So the value is on the order of 600 millivolts. That's the maximum for in-plane magnetic fields. But ignore the perpendicular field, because you hardly use that configuration for any potential applications. And these measurements are done for an AC field of 1 kilohertz. Then for the resonance, you see this one is the longitudinal resonance mode, and the values are pretty high. It's 9 times 10 power 4, that is 90 volts per centimeter Ørsted. So, it is comparable to nickel that just we saw, and this is the I believe this must be the thickness mode, and this resonance is at around 2.7 megahertz. Thickness is small, so smaller the dimension, higher the resonance frequency. That is what you see. Okay. And the values are also quite good. It is around 25 volts per centimeter Ørsted. That is okay. And you can enhance the magnetoelectric response in a composite using PCT fibers. They are specially made. So, the way they do that is, these fibers are placed between two what are called interdigital electrodes. It is like a finger pattern, and that is shown there. So, what you do is you apply an in-plane electric field to polarize these PCTs. So, what you are doing is, when you do the magnetoelectric measurements, you are using D33, not D31, because the fibers are aligned this way. The interdigital electrodes are placed in such a way that you have the electric field along the axis of the fiber, and they are poled in that direction. Then when you do the magnetoelectric measurements, D33 is the one that contributes the voltage coefficient, and then you can buy the fibers with between the two interdigital electrodes. Then you can make a composite with anything of your choice. It can be any of the 3D transition metals or alloys, and then you have to measure the voltage coefficient by measuring the voltage across these two along the between the top and bottom of the fibers. And here you see the voltage coefficient for 3 different cases. One is the traditional PCT platelet, and PCT with interdigital electrodes, and the PCT fibers with interdigital electrodes. As you see here, the fibers have the highest voltage coefficient, and the bottom one shows the resonance magnetoelectric effect, and these are also due to the longitudinal resonance mode. And look at the value here, it is close more than 200 volts per centimeter Ørsted. So, some of these are used in energy harvesting applications, but not in sensors, because the fibers with IDE, they are too long to use for sensor application. The dimension is the problem. Okay. But they could be used for energy harvesting related applications. You have seen this yesterday. These are the magnetostriction versus magnetic field for terphenol D prepared under a variety of conditions when they are exposed to different values of external stress. But what is important here is terphenol has very high magnetostriction, as high as 1400 parts per million. So, these are some of the results using terphenol with PCT. These are symmetric trilayers, and as you see here, it is comparison of magnetostriction between terphenol D and nickel. Nickel is down here, it is negative, and the maximum is around 30 or 40, whereas terphenol D has positive magnetostriction, and it is pretty high. And these are the values of the low frequency and resonance magnetoelectric voltage coefficients. The low frequency value is the peak value is around 3500 millivolts, that is 3.5 volts per centimeter Ørsted for an AC field of at 1 kilohertz. And And the resonance value is not that high, it is comparable to nickel or permanganate. Okay, so our collaborators at Virginia Tech, they came up with this idea of what they call three-phase composites. It is not really three-phase. The composite itself has terphenol D and PCT. The third phase they talk about is this manganese zinc ferrite at the input and the output arm. So, what does it do? The manganese zinc ferrite has very high permeability. So, when you apply AC or DC field, it confines the field to that particular volume. So, it directs the field along the composite. So, you do not have any leakage of the magnetic field lines away from the composite. That enhances the overall magnetoelectric effect. That is what is shown here in this data. Without the manganese zinc ferrite, you see a very shallow change in the voltage coefficient with changing bias field or constant AC field. Once you introduce the third phase, which confines the field lines through the volume of the bilayer, it has a huge increase in the magnetoelectric response that is shown with this variation. So, there are several things you can do to manipulate the magnetoelectric response by introducing a foreign material, a third layer or so on. And med glass, this is something that I want to make sure you understand. Med glass, it is an amorphous alloy of iron, cobalt, nickel and a variety of materials. They all have different numbers based on how the alloy content is. It's there is a company in New Jersey, they make the med glass alloys, and so it's probably possible to buy them. Some are restricted for export. They are not allowed to export things because they have some defense oriented applications, but some are only for civilian use. I believe that you should be able to get them if you wish, and it has very high piezomagnetic coefficient because the way the magnetostriction varies with the DC magnetic field. It quickly saturates, but the initial increase in the magnetostriction is quite steep. That makes the Q value rather high, as you see here, and that is the reason that it has very good magnetoelectric response in a composite with any ferroelectric, either PCT or PM&PT. And many of the German groups, when they did the magnetic sensors, they used med glass and aluminum nitride to make those sensors. And as you see here, this is the magnetoelectric voltage coefficient variation with the bias field. The maximum value is close to 8 volts per centimeter Ørsted, and this graph it shows the phase. There is a phase change of 180 degrees when you go from positive to negative bias field. And these are the data for the response at bending mode. This is 10 kilohertz. It's a bilayer. So, you have both bending resonance as well as longitudinal resonance. And this one shows only bending mode because the frequency is it's not very broad frequency range. It's only up to 15 kilohertz. And at bending mode, look at the value. It's close to 500 volts per centimeter Ørsted. That's quite high. And galphenol, it's an alloy of iron and gallium. It has very good magnetostriction, that's positive, and these are the values under different preparation conditions. Just ignore it. The key point here is that it has positive magnetostriction, it increases rapidly with bias field. So, the Q values will be high, and also that gives rise to a very strong magnetoelectric response in a composite with PZT. Okay. That is what is shown here. These are the magnetostriction values, lambda 11 and lambda 12, and so depending on whether it is amorphous or single crystal, the values are going to change. This is the single crystal value, and this one would be the amorphous ribbon. And here you have the magnetoelectric voltage versus frequency. The first peak is for bending mode, and the second one is for longitudinal resonance. Usually the bending mode has a stronger magnetoelectric response compared to the other resonance. And right, I showed you this slide yesterday. It's the structure of spinel ferrites with two different crystallographic sites. The ferrites are, the formula is M Fe2O4. The M is the divalent 3D ion or anything that you substitute, such as zinc, and these the trivalent ions occupy both the octahedral and the tetrahedral sides, and whereas the divalent, it could go either to the octahedral or the tetrahedral side. The magnetic structure is antiferromagnetic with unequal magnetic moment, so that there is a net ferromagnetic moment. It behaves very much like a ferromagnet for all practical purpose, and the spinel ferrites have very high Curie temperature, and the permeability, depending on what kind of substitution you have, it can change from 100 to 100,000. So manganese zinc ferrites have very high permeability. And they have very high resistivity that makes the eddy current losses at high frequencies small. So these are the preferred materials for use in any signal processing devices at microwave or higher frequencies. So this one shows what happens to the magnetostriction and the magnetization when you substitute zinc in nickel ferrite or cobalt ferrite and so on. So when you substitute zinc, it goes to the tetrahedral side, so it displaces some of the iron, trivalent iron, from tetrahedral to octahedral. So there is a net increase in the magnetization for small amount of zinc substitution. In this case, when I say small, up to 0.3, but beyond that, there is a decrease in the magnetostriction and also the magnetization, because the spin structure for high zinc substitution, it goes from collinear to canted structure. So that's the reason for this decline in the magnetization. So these are some of the data we got for bilayers of nickel zinc ferrite with PZT. Here we show, here I show the magnetostriction for pure nickel ferrite and with 20% zinc, and these are the voltage coefficient versus bias field for pure nickel ferrite, that is x equal to 0 with 20% zinc and then 40% zinc. So as you see here, the best values are for zinc substitution of 0.2, and the maximum values are around 650 millivolts per centimeter Ørsted. And right. This one shows what happens to the maximum value as a function of zinc substitution. You see the peak value for 0.2. So we also used single crystal nickel zinc ferrite that we got from collaborators, and this one is a bilayer of nickel zinc ferrite with 20% zinc and PZT, and you can apply the magnetic field along different orientation of the crystallographic orientation for the nickel zinc ferrite. these are data for the field parallel to the 111 direction and perpendicular to the 111 direction. So, when it says H parallel to 111 on the top, it refers to the plane. So, if this is the plane, the direction is perpendicular. So, this is 111 direction, this is 111 plane, and the squares, they are the values when the field is in plane, the other one is out of plane. Okay. And the maximum value is around 400. It's not anything dramatic. It's comparable to what we got for polycrystalline materials. Single crystals are rather expensive to use in any devices because it's difficult to prepare. So, it makes it rather expensive. You don't need them. You can use polycrystalline ferrites. They are as good as single crystals. This is for resonance in a bilayer of single crystal nickel zinc ferrite with 20% zinc, and since it's a bilayer, you can have bending mode as well as longitudinal modes, and the bending mode, the values are quite high. It's around, the maximum is around 45 volts per centimeter Ørsted. And the radial mode, it's also comparable to what you see here for the bending modes. And these are the peak values of the voltage coefficient as a function of zinc substitution. So, 20% zinc, that's the optimum value for the nickel zinc ferrite. These are similar data for cobalt zinc ferrites, and yeah, these initial increase followed by change in the sign. It's because the way the magnetostriction changes with the bias field. So, we also made multi-layers of cobalt zinc ferrite with PCT. The ferrite films were made by tape casting. These are 20 to 40 micron tapes, and they were laminated with PCT tapes. Then you press it under high pressure and then sinter it at high temperature, and then you have a multi-layer. These are the values for the multi-layers of cobalt zinc ferrite with different zinc substitution. The top one is for pure cobalt ferrite, and the middle is for 20% zinc, then 40% zinc. So, as you put more zinc into it, the cobalt ferrite, the piezomagnetic coefficient would tend to increase. That is what you see here. The maximum value for 0.4 zinc is around 160 compared to 50 for 0.2, and even lower value for pure cobalt ferrite. And these are the values for two different zinc substitution, 0.1 and 0.2. And the values for cobalt zinc ferrite, they are much smaller than nickel zinc ferrite. The reason being that when you calculate the piezomagnetic coefficient, the nickel zinc ferrite, they have higher values compared to cobalt zinc. So, lithium zinc ferrite, it is there is nothing preferred, it's not a preferred material for any applications, but from basic science point of view, we wanted to take a look at it, and we did, and the values here are, these are lithium zinc ferrite. We did measurements on both single crystal ferrite as well as polycrystalline and different zinc substitution, but there is nothing dramatic here. The values range from 30 to 120 depending on zinc substitution, and also we looked at the temperature dependence of voltage coefficient. If you go away from room temperature either up or down, the voltage coefficient will decrease for sure. The reason is that all the magnetic parameters, magnetostriction, piezo-magnetic coefficient, they tend to decrease for either decreasing temperature or increasing temperature. So, the best condition is operate all your devices close to room temperature as much as possible, because anything above or below, you are going to get degradation of the device performance. All right, hexagonal ferrites, I told you that they have the unique advantage of very high magnetocrystalline anisotropy field. So, you can make devices that do not need an external magnetic bias. They can be self-biased. That is the advantage of that. But on the other hand, the overall magnetostriction and the piezo-magnetic coefficient are not that great. So, their magnetoelectric response is rather poor if you compare to any composite with 3D transition metals or alloys or even spinel ferrites. So, how do you live with a better self-bias and poor magnetoelectric coupling? Okay. So, what we did, I will discuss that later on. We made a composite of, by combining spinel ferrite and hexagonal ferrite, we made a composite structure for the ferromagnetic phase. So, it has both high anisotropy as well as high magnetostriction, so that we have a win-win situation. We use that in some of the composites. That is something I am going to discuss not today, maybe tomorrow or the day after. Okay. So, there are several types of hexagonal ferrites, both M, Z and Y types. They have unique orientation for the anisotropy field. Some are along the hexagonal axis and some are perpendicular to it. So, EC axis is C axis, and those with EC plane anisotropy, that such as zinc 2Y and cobalt 2Z, they have much lower anisotropy. So, this Y, M, Z, they are all, it refers to the specific crystallographic structure. You can just ignore it, but they are hexagonal ferrites, and depending on the structure, they have different direction for the magnetocrystalline anisotropy field. Okay, so just I will show you some data, but they are not something very dramatic. The values are rather low. Now, these are the magnetoelectric response for a composite of strontium aluminum M-type ferrite with PZT. It is just a bilayer, and you see here that to start with, as you increase the bias magnetic field, the values are very small. It stays close to 0 up to 5 kilohertz. Then it shows a small increase. These are the magnetostriction, and the corresponding magnetoelectric voltage coefficients are shown here for pure strontium hexaferrite with aluminum 0.8 and 1.2. When you substitute aluminum in it, there is a small improvement in the magnitude of the magnetostriction and the piezomagnetic coefficient. That is why compared to pure strontium ferrite, and these 0.8, it shows a much higher value. But overall, the value for the voltage coefficient is rather small, but the look at the bias field for this maximum value, it is 15 kilohertz. So, if you want to put together a sensor of DC magnetic field, then you want to use something like hexaferrite, because with nickel ferrite or nickel zinc or 3D transition metals, if you look carefully at the magnetoelectric response, I want to show you quickly. Something like this, you cannot put together a sensor of DC field, because at high DC field, the voltage coefficient goes to practically 0, and you cannot make a sensor out of it to measure the DC field, whereas looking at this response, it's rather easy to put together a calibration chart, ME voltage versus bias field. Then you should be able to use this calibration to determine any unknown DC magnetic field. These are similar data for barium, aluminum M-type hexaferrite with PZT, and this is slightly better than the previous case with strontium aluminum hexaferrite. And as you see here, the best values are for aluminum 2 and barium. And similar data for other types of hexaferrites, cobalt 2Z and zinc 2Y with PZT. These are bilayers, and these ferrites have in-plane anisotropy, and they have reasonably high value compared to M-type, close to 250 for zinc 2Y and around 50 for cobalt 2Z. So, lanthanum strontium manganite is ferromagnetic below 350 degree Kelvin, and we put together composites with PZT and did the measurement at low temperature, because close to room temperature it has very low magnetostriction and piezo-magnetic coefficient. So, these are the data we got at 120 degree Kelvin, and you see there is a very fine hysteresis in the way the voltage coefficient varies with the bias field, and the maximum value is not very high, it is around 55, but it has some kind of a memory effect. So, it can be useful for specific applications related to it retains the voltage coefficient. When you increase the field then decrease it, it has a very large value at 0 bias. So, composites with pure piezoelectrics, these are not ferroelectrics. If you apply an electric field to it, there will be a change in the linear dimension along the length, width or the thickness, and they do not have any ferroelectric losses associated with traditional PZT or PMNPT, and also the low frequency magnetoelectric coefficient is proportional to the ratio of d to epsilon. These piezoelectrics have a very small d value, but also very small epsilon. The ratio d over epsilon for these piezoelectrics, they are either comparable or better than the ferroelectrics. So, for some of the applications you would rather use these piezoelectrics instead of PZT or PMNPT. So, I will discuss specific cases of composites with lanthanum gallium tantalate and the lanthanum langasite, quartz, and also the gallium nitride and gallium arsenide. So, this is LGT, and what is shown on the left is how the relative permittivity changes with frequency. This peak is because of some resonance, but if you ignore that, the value of the permittivity, the relative permittivity is close to 20 for LGT over a wide frequency range, and they have very high stability. There is no phase transition up to 1500 degrees Celsius, very high mechanical coupling factor, and the Q value for resonance is close to 100,000 or more. And the piezoelectric coefficient is rather small. It is 5 picometers per volt compared to 400 for PCT, 2000 for PMNPT. Okay. So, let us see what the d over epsilon value for these would look like. See, the d over epsilon is for LGT it is around 0.36, quartz it is 0.35, and compared to these two PGT or PM and PT, look at these values 0.12 and 0.15. So, obviously, this is a better choice compared to traditional ferroelectrics, and that is what we found in our measurements. This is with bilayer of LGT and permandur with 3 different choices for ferroelectrics or piezoelectrics. This is PGT, PM and PT, and then LGT. As you see here, these are the resonance. These are at resonance. Since these are bilayers, low frequency values are shown on the left. The resonance values are shown on the right. This particular resonance it refers to bending mode. As you see here, at bending mode, the peak value is 1000 volts per centimeter Ørsted for the bilayer with LGT compared to maybe 80 for PM and PT and around 20 for PGT. And the low frequency values for AC field at 20 hertz, and LGT has a much higher value compared to traditional ferroelectrics. And this is trilayer, so there is no bending resonance. These are resonance voltage coefficients at longitudinal resonance for trilayers with LGT, PGT and PM and PT. So, every time the LGT1 wins out, it is better than the other two. And these are the low frequency values. I just want to point out that for a bilayer, the maximum is around 2 volts for the bilayer with LGT, and for a trilayer it is 3 times that. So, if you want to put together a device, then if it is going to be useful only at low frequencies, you are better off with trilayers rather than bilayers. Okay. And this is same kind of data for LGS, langasite, and bilayers versus trilayers. It is very similar to what we saw for LGT. And these are similar data for quartz permandur, bilayer, and at bending mode, and at electromechanical resonance, that is longitudinal mode. The values are quite good, comparable to what you got for LGT or LGS. And these are the low frequency values for 20 hertz of AC magnetic field. And these are quite high values compared to what we measured for PGT or PM and PT. So, this is the comparison for all kinds of data, low frequency and resonance. So, you see here that this one shows very high value for bilayers or trilayers with LGT or quartz, and these are PGT and PM and PT. So, I will get to it later on. No, do not worry about this part. It's we built sensors out of this and looked at the magnetic noise. So, these are not important at this time. The gallium arsenide is used in several semiconductor devices. The ICs are made on gallium arsenide or gallium nitride substrates. So, we wanted to find out if you can integrate a magnetoelectric device and a semiconductor device on the same platform, because gallium arsenide and gallium nitride, they are good piezoelectrics, as good as quartz or langasite or langatite. And these are the responses we got from making nickel gallium arsenide trilayers and with PCT the comparison. Okay, so overall the gallium arsenide based trilayers show reasonably good magnetoelectric voltage, and here we see that at resonance it can be as high as 1.4 volts, And low frequency, I don't have the data here, but we got very good response even at low frequencies. To summarize, I discussed the magnetoelectric bilayers and trilayers based on PCT, PM&PT and pure piezoelectrics, and with the use of a variety of ferromagnetic phases including 3D metals and alloys, spinel and hexagonal ferrites and lanthanum manganate. And all of them show evidence for strong magnetoelectric coupling. So at the end of the day, you get the feeling that for many applications, you are better off using piezoelectrics rather than ferroelectrics. Okay. Right, thank you. Questions?
Can we avail these composites that you have been using commercially, or you have been synthesizing it in the lab?
We made them. I don't think they are commercial. I don't think so.
Like fermenter and
You can get PCT or any
but not
piezoelectric. Yeah, but
specification that you needed.
yeah, you have to put it together, and I think the key is making the bilayers or trilayers with proper bonding technique. It can change quite dramatically depending on the layer thickness that you use for bonding. And also you have to keep in mind that certain bonding may not be appropriate if the composite is going to get hard under specific application, because they will just come apart. So yes.
So with increasing electric field, why does the magnetosection go down once again in the graph that you were showing?
Which one do you remember? The slide?
Yes, the slides where the graph with electric field and magnetosection.
Was there a graph between electric field and magnetostriction?
There is no correlation between electric field and magnetostriction.
There was a graph and magnetosection was going down.
With electric field,
Some other factor. I think I'm mistaken.
So, do you remember the slide number?
I remember the slide. I don't remember the slide. Now.
okay, let's go through these. And this is one magnetostriction, and this one. So these are the values for the magnetostriction for cobalt zinc ferrite with different zinc amount, and this the very bottom one is 0.2, 0.4 pure cobalt ferrite. And these are lambda 11 and lambda 12. And for pure cobalt ferrite, it has very high anisotropy, very low magnetostriction. So until you get to 1000 Oersted, the magnetostriction stays practically zero. Then it increases. So it's negative on the lambda 12 side. It's positive. So when you substitute zinc for 0.2, the magnetostriction is it increases dramatically, and there is a huge dependence on the bias field, but it's very normal behavior. There is nothing unique about it. So did I answer your question?
So actually my question was, does magnetosection actually have a limit or
Okay, so any ferromagnet, if you apply a magnetic field, the domains will orient or grow along the field direction. So, the magnetostriction is mainly because of the orientation of the domains that involves some additional energy on the system. So, that is the reason there is a decrease in or increase in the length along the field direction. So, once you have the samples completely saturated, it becomes constant. So, there is no more increase in the change in the length. So, it saturates, that is all. But in some cases, it can go from positive value to negative. There are all kinds of variations that is possible, depending on how the domain alignment happens with the DC magnetic field. I have seen unique systems where the magnetostriction is all over the map. It goes from negative to positive and so on, because the domain will change its orientation depending on the field value and the orientation. All right, okay, thank you.